Hi, this video is about using your calculator to work out modulus of z and argument of z for complex numbers. So I'm going to do it by looking at an example, which is z equals 1 plus I. I'm going to show you how it works in a diagram and then show two different ways of doing it on the calculator. Please have your calculator with you and a bit of paper and a pen. If you don't have them, pause now and go and get them. Okay. Right. When we say z is 1 plus I, that's saying z is 1 unit across on the real axis and 1 unit up on the imaginary axis. So that's 1, and z is here. Modulus of z and argument of z are just a different way of describing where z is. And here, instead of describing it by distance across and distance up, we describe it by distance away from the origin, as the crow flies, and the direction it's in. So that's modulus of z, and this angle here is the direction, it's argument of z. Direction is measured by an angle measured anti-clockwise from the positive real axis. So complex numbers will have an argument of between 0 and 90 degrees there, between 90 and 180 there. They'll have an argument of 0 to minus 90 there, and minus 90 to a minus 180 there. Let's see if we can find these quantities. Well, you've got a right angle triangle there. So you can use what you know about right angle triangles to find them out. Mod z, you use Pythagoras. You say it's the square root of 1 squared plus 1 squared, which is the square root of 2. Argument of z, opposite over adjacent. So if argument of z is theta, we often use theta to describe angles. Tan of theta is 1 over 1, which is 1. Then we can turn to our calculator and press the shift key, press the tan key, and you see it says tan minus 1. That means the calculator is finding out not what the tan of 1 is, but what angle has a tan of 1. Put in 1. Press equals, and it says 45, and that looks right. So, argument of z equals theta equals 45 degrees. There is a snag. There's a snag. Suppose we instead had the complex number w, which is 1 unit backwards to the left along the real axis and 1 unit down, not up, on the imaginary axis. So it's minus 1, minus 1. So here, w is obviously different from z. W is minus 1, minus I. How are we going to find its argument and modulus? There's the modulus. This isn't really a problem. Modulus of w is the square root of 1 squared plus 1 squared again, and it's the square root of 2. And that looks right. Yes, it's the same as the modulus of z. But the argument of w is obviously not the same as the argument of z. W is not in the same direction as z. It's an equal distance from the origin, but it's not in the same direction. So if I rub this out, I can make myself space to mark in what the argument of w is. The argument of w is that angle, and it's a negative angle because it's clockwise. It's turning down this way, and just doing a bit of geometry there, you can see in this particular case it's minus 135. Right, what would happen if we work that out in the calculator? Well, if we work it out in the calculator, we get argument of W is theta, and tan of theta, well, it's opposite over adjacent again, which is minus 1 over minus 1, which is 1 again. So if we put it into our calculator, we will get 45. We will get the wrong answer. The right answer is minus 135, and we would get plus 45 instead. And the mystery thickens when we go to our calculator and see what tan of minus 135 is. What's tan of minus 135? That is 1. So the problem is that there are two angles which have a tan of 1, but the calculator only tells us one of them. And once we've done our tan to the minus 1 thing with the calculator, we have to look at the diagram and to see if that's the right answer. And in fact, what we have to do is look at the answer we get from the calculator, sometimes add 180, sometimes take away 180. Right, bit of a problem, bit weird. Right, there's a simple way around it. And what we do is we look for another key on the calculator, which you've got to press Shift again for, and then you press Shift to the plus key, and you see the calculator says Pol. Pol means the calculator is now going to convert across and up coordinates into polar coordinates, which just means distance and angle coordinates. So if I put in Pol of minus 1, and then I've got to do the comma, which is there, and then minus 1 again, press equals, it tells me R, which is the normal thing in polar coordinates from the distance to the origin, which is BR mod W, is 1.4142. Which is, in fact, the square root of 2 in as near as they can to decimal form. And then I have to scroll over a bit, and it says, woohoo! Theta equals minus 135. You've got the right answer straight away. So just with one key on the calculator, you get the right answer. And that's why using Pol is much easier than the way in the book. There's two snags with using Pol. The first is, you see it gives us the R as a decimal, and usually in further maths, an answer like that we would prefer to give as a surd. There are two ways around that. One, you can use the old method, the Pythagoras method, for working out mod of W. It's not hard, and just use Pol as a check. The other thing is you can get used to recognising numbers like the square root of 2 or the square root of 3. Whichever way you do it, Pol is still useful as a check. The other snag is that sometimes you want the angle in radians. In fact, quite often you want the angle in radians. You see I've done this in degrees. And I would suggest when you use Pol, you always use degrees. And the reason why is this in radians is minus 3 pi over 4. Okay, all good. However, if I'd changed the setup on my calculator to be in radians, and now I do my pol of -1 -1, I get the same R. What do I get for theta? I get -2.53619. Now, in fact, that's -3π/4. But you've got to be pretty good at recognising fractions of pi to see that that's -3π/4. So what I suggest is use pol, do it in degrees, and then if you want the answer in radians, use your calculator to convert from degrees to radians. So the big advantage of pol is it gives you the answer with just one key on the calculator, and it gives you the correct answer without any fuss. It's useful to draw a diagram. In fact, you should draw a diagram, but you don't have to look to it and see, do I have to add 180 or take away 180? The only disadvantage is it gives its answers just in decimals rather than in surds or in fractions of pi, and I've told you how to get around that. One last thing. There's a way of getting back from modulus argument to x and y coordinates, to across and up coordinates. And that is this key, if I can find it, this key, the shift, which is rec, for rectangular coordinates. So if I put in, let's test it out, if I put in rec of √2 and not 45 this time, I better not do 45, and I better make sure that I've not got that square root sign going over the comma. So I'm going to put it as pi/4, which is about 0.785, near enough. What do I get? I get x is 1, near enough, and y is 1, near enough. I get back to the original z I had. So you can use rec when you want to convert from modulus and argument to across and up. Alternatively, you can do a picture. So we've got z here described as √2 up there and 45 degrees here. And then you draw in the triangle and you say, right, this bit is √2 times cos 45 degrees, which is 1. This bit is √2 times sine 45 degrees, and that's 1 as well.